Hey, this is our last video on the equation of the plane, and we're going to be looking at the final form, which is the normal form. I thought it would be cool to start this video about looking at it in 3 dimensions, although I know you definitely all appreciate the effort I made to make you this beautiful diagram. But this is what our plane is going to actually look like in 3 dimensions. This is super cool. You can see that that's our normal there. Okay, we worked out our normal was 3i plus 2j minus 1k, and you can see it's definitely at a 90-degree angle to the plane. I mean, look at that. This is perfect. And now we're going to be looking at our final form of how to find the equation of the plane. I'm not going to go back through how to find the normal again. You guys already did that in the previous video. I'm not going to go back through how to find the normal again. We already talked about how you're going to do the cross product of the 2 vectors that lie on the plane, and you're going to find that vector here. This is the normal to the plane. So can we do this a little bit more efficiently? I think so. The proof revolved around the fact that we knew that n dotted with the vector, like the specific vector from A to P, is equal to 0. Okay? Now, we know that the vector from A to P is the vector P minus the vector A. Okay? And that needs to equal to 0, n being the normal, P being a general point on the plane, remember x, y, z, and A being the specific point we got on the plane. Well, A is not actually the point, it's the vector that would take us from 0, 0, 0 from the origin to the point we got on the plane. Now, if you are hot on your properties of dot product, you know that dot product is distributive, which means we can go like this. It works in a similar way to multiplying out brackets. Okay, so I can also move this minus n dot a to the other side. Remember, that's just a scalar quantity, so I can add that to the side. So it must be true that n dot p is equal to n dot a. Well, let's work this out and see if we get the same answer as previously. I've kind of committed a bit of a sin in the sense that I'm mixing and matching my notation here, but this one could also be written like this, and this one could also be written like this, whatever floats your boat. So let's start by doing n dot a, which is going to be, let's dot the i's and the i's. Let's write it out nice and neatly, actually. So n dot a is going to be i's and i's, 6, j's and j's, 2, k's and k's, minus 3. 6 plus 2 minus 3. So that's going to be 8. 8 minus 3 is going to be 5. Okay? Now we're going to do the other side of the equation, which is going to be n dot p. P was a general point on the line, and the vector p is the vector that would take us from 0, 0, 0 to a point x, y, z on the plane. So if I'm dotting those, it's going to look like 3i plus 2j minus k, okay, dotted with xi plus yj plus zk, which is going to be i's dotted with i's, 3x, j's dotted with j's, 2y, and k's dotted with k's, minus z. And remember, our normal form states that NA, which way around did we do it? We did it as NP is equal to NA. So let's stick with that. So our normal form of the plane is NP is equal to NA. NP was 3x plus 2y minus z is equal to NP, which is 5. So in this method, we ended up getting exactly the same answer as the previous method, but I think actually the execution is a little bit cleaner. And again, one last look at that plane. There it is, guys. I hope you found this tutorial useful. Please subscribe, please hit that like button. Let me know in the comments below which video you would like me to film next. Would you like to see more vectors or something different? Bye, guys.